Greetings, Astronomy 10, and welcome back to your Chapter 8 lecture, or your lecture on the outer solar system. That is, of course, the planets in our solar system that are beyond the asteroid belt. Obviously, in the center of the solar system is the Sun, and then Mercury, Venus, Earth, and Mars. We talked about them last time. And then the asteroid belt, of course, separates the orbit of Mars and Jupiter. Jupiter, of course, marks the beginning of the outer solar system. It is the first outer planet. And the outer solar system is a very cold place, as you might expect, it being much, much farther from the sun than we are here in the inner solar system. Jupiter's orbit, for example, is about 5 astronomical units, or 5 times our average distance from the sun. And as a result, at Jupiter's position, the sun appears 1/25th as bright. Let me see if I can draw you a picture. If you have an object like a star, right, something that's spherical, if you want to think about the light that it releases into the universe at any one given instant, it's going to release that light in all directions all at once, right? That's a sphere. And the area of a sphere is 4 pi r squared, right? Now, if we want to think about this amount of light, later on, as this same amount of light expands further into the universe, it's still the same amount of light, right? But obviously, the farther the light gets from the source, the dimmer it's going to appear. And this is something that we all have experience with, right? We've all seen headlights at a distance, or, things like that, for example. But by how much? Well, if you want to think about this constant amount of light, right? The amount of light that's on this sphere is going to be on this sphere sometime later. And if you want to think about the area of this sphere compared to the area of this sphere, let's say that the radius of this sphere is 1, and the radius of this sphere is 2, right? How much bigger is the surface area of this sphere? Well, 4 pi times 1 squared is 4 pi, right? 4 pi times 2 squared, 2 times 2 is 4, 4 times 4 is 16. And so the surface area of this sphere is 4 times the surface area of this sphere, even though the radius only increased by a factor of 2, right? Because the area depends not on the radius, but the square of the radius. So, if you want to think about, say, the light that comes out of like a light bulb, right? At a distance of, say, 10 meters, let's say that if you wanted to look at like a certain slice of the light that came off of this light bulb, at a distance of 10 meters, let's say this amount of light covers a screen that's 1 meter on a side, so 1 square meter, right? What does that mean? Well, at a distance of another 10 meters for a total distance of 20 meters, what size screen is it going to cover at that distance? Well, instead of being 1 meter on a side, it should be 2 meters on a side, right? So 2 meters by 2 meters. That's 4 square meters, right? 2 times 2 is 4. And so, if you double the distance, the light is going to appear 1/4 as bright, or 4 times as dim, if you want to think of it that way. Which is why, at Jupiter's orbit, which is 5 times our orbit, the sun appears 1/25th as bright, right? And so, out there in the outer solar system, the sun does not appear nearly as bright, and so it's not nearly as warm in direct sunlight. Here on Earth, the sun looks like a very, very bright star, right? Very, very bright. It's incredibly bright, even in comparison to our own sun. Um, or I'm sorry, in comparison to every other object in the sky. Obviously, the sun is much, much brighter than everything else. The moon, our own moon is what I meant, and all the other stars in the sky, the other planets, and so on. And while the sun still appears bright, it's not 500 times brighter than our own moon as it appears here on the surface of the Earth. Out in the outer solar system at Jupiter's orbit, it's much, much dimmer. And then, of course, at Saturn's orbit, at twice that distance, it's a hundredth, all right, yeah, 10 times 10, right? It's a hundredth as bright as it is here on the surface of the Earth. One of the first images in our image bank today is a table of sort of useful quantities in order for us to try to make sense of the outer planets and their major characteristics. And some of those, like the mass and the radius and so on, those were sort of a challenge to try to figure out because they're not exactly close to us, right? Obviously, we had to use some advanced techniques in order to figure out the size of these planets because they're really far away, but they're also very large, right? In order for us to figure these out, originally we used what we call stellar occultation. If one object kind of goes in front of another object and blocks out our vision of this object, we call that an occultation, when something goes in front of something else. We talked a little bit about that before. And what we do is we look at a star that's really, really far away, something that has no what we call measurable parallax. Stars that are closer to us will have a certain amount of measurable parallax. And what that means is if we take a picture in, say, January, and then we take a picture in July 6 months later when we're at the other end of our orbit, if it's close enough to us, if the star is close enough to us, it'll appear to have moved a little bit compared to distant background objects. For the same reason that we have depth perception, right? If we're looking at from two perspectives that are laterally separated a little bit, like our eyes, an object that's close enough will appear to shift a little bit in one eye compared to the other, or in one picture from January compared to the picture from July. But if we're talking about an object that has no measurable parallax, if it's really, really far away, right, that it doesn't appear to move at all, no matter when we take pictures of it, we can use that to determine the size of a planet by looking at this star, and then when the planet goes in front of it, right, we can tell how big the planet is by how long it takes to move in front of it. We're able to tell how fast it's moving, of course, its orbital velocity, because of Kepler's laws of planetary motion, right? Obviously, the closer a planet is to the sun, the faster it's going to move. And we can tell the orbital period also because of Kepler's third law, right? If we know the orbital distance, we can solve for the orbital period, right? And we can also use Kepler's third law. Actually, we have to use the astrophysics version of Kepler's third law, which includes the masses of the planets, or in this case, the mass of, like, Jupiter and one of its moons, in order to determine the mass of both of these bodies. We'll talk a little bit more about that when we talk about looking for the masses of stars. But suffice to say, we can use Kepler's laws in order to determine the masses of these planets. This technique only works for planets with moons. But fortunately for us, the planets in the outer solar systems all have tons of moons. Jupiter especially has a holy mess of moons, 60 some odd moons. And those are just the major ones, of course, not like the little asteroid ones or whatever. Obviously, when people started trying to solve this out in like the 60s and 70s, we had limited technology and precision for these measurements, and now that we've actually sent probes past them and measured the planet's gravity, we've got a better estimate, a more refined measurement of the size and the mass and so on of these planets. Some other interesting things. Jupiter has a 3-degree tilt, meaning it has basically no seasons because it has no polar region. But of course, seasons on a gas giant is a little bit different than on a planet you can stand on. If you look at the density of the planets, most of them are about 1.5 or below. The exception, of course, being Saturn, which is much, much lower. Saturn is actually less than 1 water density compared to the other planets, the other gas and ice giant planets in the outer solar system. It's very, very low. And in theory, if you could find an ocean that was large enough and you dropped Saturn in it, it would float. And it doesn't really quite work that way because it's made out of gas. And so, if it collided with an ocean, it would probably deform some. But suffice to say that it's less dense than water. And that's very different compared to the inner solar system, where, if you remember, most of the terrestrial planets are about 4 times the mass, or the density, excuse me, of water or more. The outer solar system, obviously the planets there are much, much farther than they are in the inner solar system. Jupiter is about 5 AUs, Saturn 10, Uranus and Neptune about 20 and 30 respectively. So they're very, very far, and as a result they're very, very cold by our standards, right? And because they're made up of gas, not only do they rotate very quickly, the gas giants, Jupiter and Saturn, are both about 10 hours, and Uranus and Neptune are both about 16 hours. And so they have very short days. But not only do they have very short days, they also rotate differentially, kind of like the sun does. We'll talk more about that soon also. But if you wanted to talk about Jupiter, right, everybody knows what Jupiter looks like, right? It has this great red spot, we call it. It moves faster at its equator than it does near the poles, right? And in the middle, it's faster than it at the poles, and not as fast as at the equator. And if you've ever seen the surface of Jupiter, like if you look at a picture, you can see that there are kind of bands in it, and it's for this reason, because of the differential rotation. The composition of all the planets. Oh, actually, one other note on the differential rotation. Because of this, they kind of bulge out at the equator because there's more momentum there, right? So they're not perfectly spherical. In any case, the composition of these planets are pretty similar to the composition of the sun, because, spoiler alert, they all came from the same cloud of gas that made everything else in our solar system. No surprise, right? Thus, the gas and ice giants are mostly hydrogen, like the rest of the universe, with a healthy dose of helium, about 20 to 25%, like the rest of the universe, but with a smattering of other elements, like what we would find in the sun and indeed the rest of our solar system, but not necessarily every other solar system in the universe, right? Now, if you fell into a planet like Jupiter, what would happen? Well, Jupiter's made out of gas, right? Mostly hydrogen gas, which is why we call it a gas giant. And so if you fell into this planet, you would be falling through gas, like several Earth diameters of gas. You'd be falling a very, very long time. But you would fall, and the gas would become denser and denser and denser, like falling into a thick fog that got thicker and thicker and thicker until, it started to become like, from fogs, it would become like rain clouds until it would become like really, really dense. And then eventually it would just kind of seamlessly become liquid because of the increased density. And that, of course, is because of gravity. But eventually you would fall through so many kilometers in Earth diameters, right? You'd be falling a very, very long time. And because of the increased density of the material, your terminal velocity would decrease, right? You just kind of keep falling slower and slower because of all the gas and liquid particles that you're knocking up against, right? That you're coming into contact with. That eventually, after falling through several Earths, you fall through gas and then fall through liquid, and then eventually you would come to a point where the liquid becomes so dense that it can conduct electricity. We call that liquid metallic hydrogen. And then eventually you fall all the way to the middle where there's kind of like a solid core. The pressure at the core is probably something like 45 million times the atmospheric pressure here at Earth's surface. So 45 million atmospheres of pressure. And at that point, it's so hot that it can be up to like 35,000 Kelvin, which is almost like 35,000 degrees C. If you remember the Kelvin and the absolute temperature scale, the difference in between Kelvin and centigrade is an offset of 273.15 degrees. So this intense amount of pressure keeps the water from turning into steam, and eventually essentially what happens is you have like a convection current that brings heat from the core out to the surface where it can kind of radiate out into the cold void that is space. Now, there's no volcanism in a gas giant, right? There's a little bit of tidal heating, maybe a tiny little bit, because of the moons, but compared to the entire mass of the planet, there's not a lot, not enough to heat it from friction, right? And so mostly, Jupiter gets its heat influx, right? Its heat input from the sun. But because Jupiter is so big and it has such a massive surface area, it's radiating heat more quickly than it's absorbing heat from the sun. As a matter of fact, almost twice as much, about 1 2/3 or 1.67 times as fast as it's absorbing heat, and as a result, Jupiter's actually shrinking. It's not shrinking very fast, of course. In about 1 billion years, it will have shrunk about 1%. And so we're not in danger of losing Jupiter or losing the visual appearance of Jupiter even. The core that I mentioned earlier at the center of Jupiter is very massive, probably somewhere between 10 and 20 times the mass of the Earth for Jupiter, and actually for Saturn too, actually probably falls within that range. The Great Red Spot, this really, really big thing, this surface feature that has probably been there since, Galileo looked at Jupiter, some 300 years ago or whatever. It's been there for at least that long, probably much, much longer. And if we look at the swirling edges of this tremendous cloud, we can see that it looks like a tremendous whirlwind, like a hurricane. And it's so big, actually, that it takes about a week for it to rotate. 7 days. And it's so large that you could fit 2 Earths in it side by side. It's real, real big. And it doesn't show any signs of slowing down or going away. It's probably going to be here for hundreds, if not thousands of years more. The atmospheres of the outer planets contain elements and compounds that only condense out of the molecular cloud that made our solar system at low temperatures. Remember, these things we called volatile materials. On Earth, only water can condense with our atmospheric pressure. But the gas giants make much more volatile materials in their clouds. Uranus and Neptune, of course, have this blue appearance because of the methane and the methane ice in their atmospheres. Now, Jupiter is not volcanically active, and so it's tempting to think that it might not have much of a magnetosphere, but because you have that many particles that are moving, all these gas particles, right, all moving together, it actually has a tremendous magnetosphere or magnetic field. So much so that it extends all the way out to the orbit of Saturn, which is about twice as far as Jupiter is from the Sun, or 10 astronomical units. So Jupiter is at 5, and its magnetosphere, because it's being pushed away from the Sun, right, because of the solar wind, its magnetosphere goes all the way out to Saturn's orbit at 10 astronomical units. It's real, real big. It has the largest, by far, magnetic field of any planet in our solar system. It's tremendous. Now, because it has such a strong magnetic field, it actually has an aurora, similar to our own aurora borealis and aurora australis, like we have here on Earth. When the Voyager 1 probe encountered Jupiter's aurora in 1979, it found particles that were something like 300 million Kelvin, or about 300 million degrees C. Fortunately, this aurora was diffuse, right? Very sparse. And as a result of it being sparse, the probe was able to escape through its contact with the aura without any sort of damage or going haywire or whatever. A few years before that, in 1974, when the Pioneer 11 mission encountered Jupiter's radiation belts, it picked up something like 400,000 rads of radiation. And if you've ever played like any of the Fallout games or anything like that, you may have some sense of what rads are or how much energy is in a rad. But suffice to say that 400,000 rads is 1,000 times a lethal dose of radiation for a human being. It's a lot. Now, all of the outer planets have ring structures, and we'll talk a little bit more about rings at our next lecture. But let me just talk a little bit about why it is rings exist and why all the outer planets have them. First of all, there's a lot of material floating around in the outer solar system. Chunks of ice, rocks, and stuff left over from the early solar system, and so on, right? Now, let's say you have a planet, like Jupiter or whatever, and you have one of Jupiter's moons. Obviously not to scale, right? But let's say there's like an asteroid here. And actually, let me draw it so it's like directly on a line between them. Okay? Obviously, Jupiter's gravity is going to pull the asteroid toward it, and the moon is going to pull the asteroid toward it, right? There's going to be a tug of war. And if it's in just the right spot, the forces can equilibrate, right? Like this force of gravity will equal exactly this force of gravity. And it's not actually stable there because, you know, everything is revolving about this planet, but it's kind of stable, right? If this was, say, the Earth and the Moon, there's actually like a cloud of dust. New particles of dust come all the time, and new particles of dust leave all the time. They call it the Gegenschein. But this is the L1 Lagrange point. This is one of the points where gravity and momentum kind of cancel out. And it turns out that for two orbiting bodies, for a two-body system, there are actually 5 Lagrange points. The Trojan asteroids, for example, all kind of float at one of the Lagrange points. If this was like the Sun and Jupiter, there's like an asteroid belt here. There's 2 points that are like where there's an equilateral triangle. Actually, that would make that point here. And the asteroids that are there all kind of make a stable orbit relative to Jupiter and the Sun. Yeah, we call those the Trojan asteroids, and they kind of occupy 2 camps. But in any case, obviously, there's a point here where gravity equilibrates. And that means anywhere kind of in this area here, if the asteroid goes anywhere in here, then it's going to be dominated by the planet's gravity, right? And then if it goes anywhere in here, it's going to be dominated by the moon's gravity. We call these Roche lobes. Roche is R-O-C-H-E. And if there's an asteroid here, and I'm going to kind of blow this up a little bit so we can kind of get a better view of what's going on here. So here, in the asteroid, I'm going to draw just a little bit larger. Obviously, the planet's gravity is going to pull it this way, and the moon's gravity is going to pull it this way. And if these tidal forces are greater than the gravity that's holding this thing together, what's going to happen? Well, it's going to shred it, right? It's going to rip it apart. And so all of these particles, you know, that make up this ice comet or whatever it is, are going to get ripped apart, and they're going to go into their own orbit around the planet and make a ring. And that's why rings exist, because the gravity or the tidal forces exceed what we call the Roche limit. Anyway, we'll talk a little bit more about rings and moons next time. But suffice to say that now that we talked more about the outer planets and the inner planets, you should know what all the planets are and their names. That's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And so I want to introduce to you your first piece of mnemonic homework, and that is to write a mnemonic to remember the names of the planets in order from the Sun to the outer solar system. Of course, Mercury is the closest, right? Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune going towards the outer solar system. I'm congested. In any case, you want to start with Mercury and end up with Neptune. And what you want to do, you have maybe a little bit of leeway, but in theory you want to have like an 8-word phrase, and each one of the words starts with the names of one of the planets, right? The classic one that everyone uses is something like, "My very eager mother just served us nachos." So obviously don't use that one, okay? I want you to write your own, and obviously you have to submit your own. This is not a group project. You write your own, you submit it to the assignment page, okay? Let me be very clear. If you use something like "My very eager mother just served us nachos," you do not get credit for this assignment, okay? If it's close to that even, if you change just like 1 or 2 of those, still no credit. Okay, end of story. No excuses. Now, what I'd really like for you to do is just sit for a little while, be creative, come up with your own idea. I promise you, you will come up with one sooner or later, okay? The funnier ones that people submit, I will read anonymously to the class. The best one that I had, I think this was from my first semester teaching astronomy at Evergreen, was "My Viagra elevates my junk superabundantly, uglies notwithstanding." It's pretty good, right? But you want to come up with your own in order to receive full credit for this assignment. Okay, that's about it for Chapter 8 and the outer planets, the gas giants, Jupiter and Saturn, and the ice giants Uranus and Neptune. And I hope you have enjoyed this lecture as much as I have giving it. I'll see you next time.